Hello, my name is James Leach and welcome to this video focusing upon memory as you need to know it for the MCAT. In this video, you are going to be solidifying your understanding of four major components of memory. First, how are memories encoded? How do they get into your head? Second, once they're in there, how are they stored? Logically then, because you're bothering to store these memories, you will want to call upon them eventually. So how do we call upon our memories? How do we retrieve our memories? And lastly, everyone knows our memories are not perfect, so we're going to be tying our memory review together by identifying some common errors in human memory. Across those four topics then, our goal is to forge connections between encoding, storage, and retrieval in order to build a picture of a fluid, flexible process. Along the way, we're going to solidify our understanding of the various types of memories because, as you're aware, not all memories are created equal. Take a look at this enormous molecule in front of you. There are people in this world who could reproduce that from memory, and you may even be one of those people. Don't worry if you're not, you will not be tested on the structure of gastrin. You may, however, be tested on how someone could come to memorize this entire structure. So let's situate ourselves at the start of the process. We are constantly being bombarded with information from our environment. We have five senses pulling in information every waking millisecond. Some of that information we remember. Sometimes we don't try to remember it, but it happens anyways through automatic processing. The term automatic indicates that there is no conscious effort going into the formation of that memory. For example, you may remember if it was cold yesterday, or if it was hot 2 days ago, or if it was snowing this morning, but odds are you didn't have to tell yourself to make an effort to do so. At the other end of the spectrum, where all you MCAT warriors are investing your time, is into effortful processing. That is, making a conscious effort to remember something. For example, endocrinology takes some conscious effort to remember. Of course, it's not always this black and white. When it comes to playing a new sport, there's a lot of effortful processing that goes into mastering these complex behaviors, but once you get it, the processing becomes automatic. Now, not all stimuli coming into our brain are treated equally. That is to say that certain situations or types of stimulus are more conducive to being remembered. One way we often try to remember things is by picturing them in our head. This occurs via the process of visual encoding. In order to remember something based on visual stimuli alone, you visualize it to encode the image. However, this is at the weaker end of the spectrum in terms of encoding memories. We can also remember things by the way they sounded or by hearing someone explain them orally. Something passing through short-term echoic memory is the beginning of encoding the way something sounded. These memories are slightly more robust than the mental images we store. If you watch a football game on TV, you see it and you hear it. You can visually encode the images that pass on the screen and remember the sounds you hear. However, most people don't remember a whole lot about most of the things they watch on TV. On the other hand, semantic encoding is the process by which memories fit into a certain context or carry a particular meaning. When you study, you may employ mnemonics to fit the stuff you want to memorize into a contextual framework which is more memorable than the information standing on its own. This is why it's so important to stop and think about what you read. Fitting it into a framework, into a meaningful context, makes the encoding of memories far more powerful. This is why success in your MCAT studying depends so much on practice. Going a step further, things are encoded even more robustly when we, the egocentric creatures that we are able to implicate ourselves in the memory or tie it back to ourselves. This is called the self-reference effect. We form more conceptual connections and do more processing of information which we view as being related to ourselves. Back at the football game again, the quarterback or a member of the marching band is going to remember that game far more vividly than someone watching at home because those memories not only carry a very specific meaning for them, but also because it was a significant event at that point in their life and everything going on that day ties intimately back to their own personal experience. There are a number of things that people do in order to take advantage of this hierarchy of encoding. Many things that you probably do every day. How many times have you gone to the grocery store to get a few quick items and simply repeated to yourself, milk, bananas, bread, milk, bananas, bread, milk, bananas, bread, without making eye contact with anyone, just repeating it so many times until the words basically meant nothing to you anymore? This is called maintenance rehearsal. It can be done to keep something in working memory or short-term memory, and can also be an effective way to encourage the storage of long-term memories as well. The process of actively repeating or rehearsing something makes it all the more memorable because of repeat exposure to the stimulus. Mnemonics are another invaluable way of grouping together information to contextualize it in order to remember a group of items under one umbrella term. This is particularly useful for committing lists of information to mind. For example, the anterior pituitary hormones, which are far more easily remembered as a mnemonic that you may use when studying endocrinology, flat peg, than as a convoluted list of hormones. And this leads to clustering or chunking, which is the process of remembering things in chunks as opposed to long lists. If you had to remember this list of letters, it would be far more effective to read it backwards and remember 4 items: bus, car, truck, plane, than to remember 16 unrelated items. That's encoding. The stimulus has gone in one ear, but how do we ensure now that it doesn't go straight out the other, as the old idiom goes? Well, that depends, again, upon the type of information we're receiving and how our brains parse that information. Our most fleeting type of memory is sensory memory. You can try, but it's pretty difficult to remember that 3x3 set of letters without rehearsing it or thinking about the groupings of letters. If you just take a snapshot and close your eyes, your visual image fades surprisingly quickly. That's your iconic memory, the brief snapshots your brain takes of everything you see. Echoic memory serves an analogous function with auditory information. If you don't do any extra work with the auditory input you receive, such as repeating or rehearsing or developing mnemonics, it will likely go in one ear and out the other. Slightly more robust than our sensory snapshots is our short-term memory. If I asked you to look away now, would you be able to dial that number? It's quite possible that you could. The 10 digits are split into 3 chunks, and this number would obviously have some practical value to you if someone is sharing it with you. Again though, everyone is probably very familiar with thinking, oh, I don't need to write that down, and then having to ask the person to repeat the number shortly after. Short-term memories fade quickly without rehearsal. Our brains do a slightly better job of holding onto working memory, as information like 67 plus 2 minus 15 times 3 is not only a block of digits, but it draws our attention as well. That block of digits has an executable function that our brain can focus in on and try to solve. Working memory is more robust than sensory or short-term memory because it integrates attention and function. Our brain holds onto this information because it is actively doing work with it, then lets it go shortly after the work is done. Of course, some of the things we hold in short-term memory must be summoned in order to perform operations on them in working memory. However, our goal when studying or when reading about topics we're interested in is to commit the information to long-term memory so that we can access it later. These long-term memories, the memories we can keep for a lifetime, are further subcategorized. We store explicit memories, which are ones that we can recall on demand. Explicit memory is interchangeably referred to as declarative memory, which again is a collection of the things we can consciously recall, such as facts and events. Declarative or explicit memory is composed of 2 important subtypes. The first is episodic memory. We are capable of recalling a wide array of episodes in our lives, or events and experiences in our lives. These are not the things we studied for or tried to remember. Those fall under semantic memory, our memory of facts and concepts. But we don't always consciously dredge things up from the depths of our memory. The term muscle memory, for example, is very popular. The idea that your muscles remember what to do if you just let them go. Of course, we know that memories aren't actually stored in muscles, but implicit memories are the ones that we do not require and sometimes we do not have conscious access to. An activity such as riding a bike calls upon our procedural memory. These are blueprints for skills and tasks that are engaged under the right set of environmental stimuli. For example, getting onto a bike and hoping that it goes. Do you remember the last time you rode a bike, or the first time maybe? That's episodic memory in action. And what are those big round things on the bike, or the place you put your feet? If you said wheels and pedals, your semantic memory is to think. If you were to get on this bike and you were capable of riding it based on previous experience, your procedural memory deserves the credit. As in the case of riding that bike, your memories are worthless if they serve no function, and they serve no function if they can't be retrieved. Our memories can be accessed in a variety of ways. So-called relearning is the process by which something we've already learned is much easier to learn again at a later time. Thus, cramming for tests is not the optimal way to be studying. Ongoing studying is the best way to develop long-lasting, robust knowledge. Recall is just as it sounds, the statement of previously learned information. Free recall is a matter of remembering something and being able to summon it at will or when prompted. If I asked you to provide the names of 50 people from your graduating class in high school, could you do it? Maybe you could get to 50 by free recall, but it wouldn't exactly be easy. Recognition is sometimes referred to as cued recall. When given a clue, so to speak, an individual can remember pieces of information that they may otherwise not have been able to recall freely. For example, if you didn't think you could get to 50 names from your graduating class on free recall alone, what if you had the pictures from the high school yearbook? The cues provided by seeing people's faces will lead you to recognize more than you otherwise would have recalled freely. And we can explain why seeing someone's face, as in the yearbook example, would activate a memory of their name. Semantic networks are the networks which come into play in order to explain this phenomenon. If I said the word fire engine to you, you probably wouldn't summon up a perfect schematic of a functioning fire engine, but you will conjure up the image of a vehicle, and as such, the network for vehicles, or things on the street, experiences activation. Similarly, the network for the color red is activated as well. This is a concept called spreading activation, which lies at the heart of priming, or preparing the brain to recall one thing by feeding it something related, as in the case of showing a yearbook picture to elicit a name you otherwise may not have remembered. Priming of semantic networks, however, is but one phenomenon which affects our ability to recall information. The location in which information was learned is the best place in which to recall that information based upon context effects. If you learn something underwater, it is likely that you will more successfully be able to recall it when underwater. Playing into that same idea, having the same mental state during recall as you were experiencing during encoding increases the likelihood of remembering that information. This phenomenon is called state-dependent memory. Both of these concepts are offshoots of priming. If all of the physical stimuli around you are the same as they are in that memory for which you are searching, the networks surrounding that memory are going to be more accessible and more active. Similar to priming, but not to be confused, is the primacy effect, which goes along with the recency effect, and both fall under the umbrella term of serial position effects, which dictate that things you are told or things you see first and last in a list or array of items will be remembered better than those items in the middle. Take this list of letters, for example. If a group of people were asked to recall that list, A and V would be the most reliably recalled letters in that array. These three effects lead nicely into identifying how mistakes are made by our brains or how things are forgotten. And let's face it, we can't remember everything forever. Aging and memory dysfunction as a result of neurological disease or injury are major causes of memory impairments in humans. Dementia is the most common age-related neurological disorder which erodes memory. Looking at the brain of an Alzheimer's patient, one can see the extensive damage done by the aberrant deposition of unwanted molecules throughout the brain. Destruction of neurological networks is destruction of semantic networks, as the neurons are what encode those semantic networks. However, one does not need to be afflicted with a disease nor be of old age in order to forget something. We've all been there 1,000,001 times. The so-called curve of forgetting reveals robust psychological effects that have been seen repeatedly over the years. The longer you go without revisiting a memory, the more likely it is to be forgotten. This is called decay. Beyond just decay, though, we all experience what is called interference, where the formation or retention of memories actually depends upon your other memories. For example, if you've ever moved within the same city and you receive a new postal code or new zip code, they're often quite similar to the old one. At first, remembering the new one may be tough because of proactive interference. That old code is similar to the new one you're trying to remember and prevents it from being easily encoded. However, after a while, that new one sinks in and retroactively interferes with your memory of the old code. Furthermore, the memories we do have may not be entirely accurate because they can be aberrantly constructed. Since our brain does not record and store memories in the same way that a video camera does, there are big gaps in our memories of events. The brain, in an honest effort to make sense of these things, takes the liberty of filling in those gaps in our memories with things that seem to make sense, whether or not they actually happened. This is how false memories are created by the process of confabulation. Another trick we're susceptible to is the misinformation effect. New information, true or otherwise, about an event affects our ability to effectively and accurately remember that event. The misinformation effect is the major reason why eyewitness testimony is notoriously dubious. As if that wasn't enough, there is also source amnesia, wherein an individual conflates semantic memory and episodic memory by losing their picture of the context under which the memory was encoded. For example, people can believe that something that happened to them in a dream actually happened to them in real life because the context of that memory was forgotten or incorrectly encoded. Now let's tackle a couple of practice questions in order to activate your semantic networks surrounding the topic of memory so that the information will be easily retrievable on test day. First, take a look at this question which brings back Pavlov's dogs. When Pavlov rings the bell, the dogs begin salivating because they've been conditioned to automatically summon the image of food upon hearing the bell, a subconscious association formed by experimental manipulation, which means that it must be an element of implicit memory. Here's one more practice question, this time referring back to sensation and perception. In this case, the student thought of a seemingly unrelated object in order to activate the semantic network around that object, which includes the three colors, red, green, and blue. This student capitalized on the role of semantic networks in human memory. In this video, we began our exploration of human memory by delineating how information enters into memory through iconic and echoic pathways. From there, we identified the many ways in which information can be stored and how long it is able to stay there. Of course, memories are useless if they can't be revisited, so we also identified how things that have been remembered can be brought to bear again and used in our everyday lives. Lastly, we uncovered the ways in which memory isn't perfect, how memories can be lost, and how they can be downright wrong. Thanks for watching this video on human memory. Not only have you deepened your knowledge of a topic that will be tested on the MCAT, but you've also had a glimpse into the workings of your own brain as you're at home preparing for the test.